Hello everyone and welcome to the presentation on the topic Basic Properties of Nucleus and Nuclear Forces. Now, before you dive into the vast ocean of nuclear physics and learn about the salient features of radioactivity, radioactive disintegration, decay constant, radioactive equilibrium, and whatnot, it's really important to first lay a good foundation, and that's exactly the aim of our presentation. Our presentation on the topic Basic Properties of Nucleus will give you a detailed understanding about the nucleus and its properties. We will also be discussing the various nuclear forces that are present in the universe. Now, before we go any further, I would like to introduce you to my group members, Leya Saju, Ria Rose, Anne-Marie George, Aneena Maria, and myself, Swathikedini. We are deeply honored and blessed to be mentored by Dr. Pius Augustine, Department of Physics, Safeguards College, Devra. Now, these topics are not at all difficult to understand. Some of you might have learned this already, and it's just a revision for you guys. So, I invite Leya Saju to come forward and start the presentation. Leya, please.
So, first we can look into the basic properties of nucleus. The basic properties of nucleus are listed here. They are nuclear charge, nuclear size, nuclear mass, mass defect, binding energy, nuclear fission and fusion, packing fraction, nuclear density, nuclear spin, and finally magnetic moment. Let's discuss these one by one. First property is the nuclear charge. We all know that nucleus contains nucleons, that is, nucleus contains protons and neutrons. Neutron is neutral and proton is positive. In the figure, protons are yellow colored, which is positively charged, and neutrons are orange colored, which is neutral. So, the overall charge of nucleus is positive. Charge of an electron, we know it's negative 1.6 into 10 power minus 19 coulomb. The charge of a proton has the same magnitude, that is 1.6 into 10 power minus 19 coulomb. Total number of protons in an atom is equal to the atomic number, and atomic number is represented by Z, and charge of each proton is positive E, that is positive 1.6 into 10 power minus 19 coulomb. So, the charge of nucleus is Ze. But when considering atoms instead of nucleus, electrons also come into play. Electrons are revolving around the nucleus, which is negatively charged. There is equal number of positively charged protons and negatively charged electrons in an atom. So, they get cancelled and overall charge of an atom is neutral. Next, we can discuss about nuclear size. In the introduction part of vector atom model, we studied about the alpha scattering experiment done by Rutherford, which led to the discovery of planetary model of atom. That model gives us the idea that nuclear volume is a very small part of the total volume of atom. And nuclear radius is of the order 10 power minus 14 meter to 10 power minus 15 meter. Nuclear radius is represented by the equation R is equal to R0 a power 1 by 3, and R0 is 1.2 femtometer. 1 femtometer is 10 power minus 15 meter. So, R0 is 1.2 into 10 power minus 15 meter, and A is the mass number. Next, we can discuss some questions related to nuclear size. First question, by what factor must the mass number of a nucleus increase to double its volume? So, the question is, to double the volume, how should we change the mass number? Nucleus can be considered as a sphere. So, volume of sphere is 4 by 3 pi r cube, where r is the radius of sphere or nucleus. In the previous slide, we studied the equation for radius of nucleus as r is equal to r0 a power 1 by 3. So, volume V is equal to 4 by 3 pi r cube can be written as V is equal to 4 by 3 pi r0 a power 1 by 3 the whole cube, which is equal to 4 by 3 pi r0 cube a. So, we can see that volume is equal to 4 by 3 pi r0 cube a, where 4 by 3 pi r0 cube is a constant. So volume is directly proportional to mass number. Thus we came to our answer: when mass number is increased twice, volume is doubled. Second question is, by what factor the mass number of a nucleus increase to double its radius? So the question is, to double the radius, how should we change the mass number? We know the equation of radius of nucleus as r is equal to r0 a power 1 by 3. Multiplying the mass number by 8, r1 is equal to r0 into 2 cube a the whole power 1 by 3. Then r1 is equal to r0 into 2 a power 1 by 3. That is, r1 is equal to 2r. So when mass number is increased 8 times, radius is doubled. I hope everybody is clear with nuclear charge and nuclear size. Now I invite Swati to continue with the remaining properties of nucleus.
So much, Leya. It was a wonderful presentation. So I'll be dealing with the topics of nuclear mass, mass defect, and binding energy. So let's start. The nuclear mass, as the name suggests, is the mass of the nucleus. So all of us know that the atom consists of protons and neutrons at the center, known as the nucleus, and the electrons, they revolve around the nucleus. So in a sense, the nuclear mass is the mass of the protons and neutrons. And this nuclear mass in atomic units is very close to the mass number A, but it's not the same. It's close, but it's not the same. I'll tell you the reason. So all of us know the definition of 1 AMU or 1 U. So 1 atomic mass units or 1 U is equal to 1 by 12 the mass of a carbon-12 atom. Now, a carbon-12 atom consists of 6 protons and 6 neutrons, and thereby making 12 nucleons. So by this definition, we can come to the conclusion that mass of 1 proton is 1 U and mass of 1 neutron is also 1 U. But in reality, when we measure them to a very high degree of accuracy, we find that mass of 1 proton is almost equal to 1.007 U, and mass of 1 neutron is almost equal to 1.008665 U. So here you can see that the mass of neutron is greater than the mass of proton. And I'll tell you the reason towards the end. But now, just by looking at them, we can see that there isn't much of a difference between them, right? So, but you have to realize that we are dealing with things at the atomic level. So such slight variations can have a huge impact. Also, the mass of 1 electron is nothing compared to the mass of protons and neutrons. It's just 0.00549 U. Now, let's take an example. The helium atom. It consists of 2 protons, 2 neutrons, and 2 electrons. So its mass should be equal to 2 times the mass of proton plus 2 times the mass of neutron plus 2 times the mass of electron. And if you calculate this, you will get the value to be 4.032980 U. So this is the calculated mass. But in reality, if we measure the mass of a helium atom using various spectroscopic techniques, we can see that the actual mass of helium atom was found to be around 4.002603 U. So here we can see that there is a difference between the mass that we expect and the actual mass of the atom. And this difference in the mass is what we call as mass defect. So, by definition, the mass defect is the difference between the mass of an atom and the mass of its individual particles. So just now we saw that the actual mass of helium atom was less than the mass of its constituent particles. We also have an equation for mass defect, that is delta M is equal to ZMP plus A minus ZMN minus M, where delta M is the mass defect, Z is the atomic number, MP is the mass of a single proton, A is the mass number, and Mn is the mass of a single neutron. So A minus Z gives us the total number of neutrons. So in a sense, the fact right here is that MP plus A minus Zmn is the calculated mass and the M is the observed mass. So now let's calculate the mass defect of the helium atom. The mass defect of helium atom delta M is equal to calculated mass minus the observed mass, that is 4.0329980 minus 4.002603. That is equal to 0.0303774 U. So this is the mass defect of helium atom. Now, if you look at this picture, we can observe that the total mass of the constituent particles is more than the mass when these particles are in the nucleus, and this is always the case. So obviously a question occurs. Why is it like this? Why there is a difference in mass, and more importantly, where does this mass go? Okay, so just now we saw that if you take protons, neutrons and electrons and shove them into a nucleus, the mass is lost. We also know that if mass is lost, then it has to be converted into energy from Einstein's famous equation E is equal to mc square. Now, if mass is lost, that means energy is lost. And this means that when constituent particles come together to form an atom or a nucleus, energy is released. We can also look at it the other way. If we were to break this nucleus right here, we have to supply energy, right? So this energy that comes into play is what we call as binding energy. And the equation for binding energy is E is equal to delta mc square. So by definition, binding energy is the energy required to separate a nucleus into its constituent particles. It can also be defined as the energy that is released when the constituent particles come together to form an atom or a nucleus. And we already saw the equation that is E is equal to delta mp square. Now, binding energy determines the stability against disintegration, meaning if binding energy is large, it means that a high energy is required to split the nucleus and the atom is more stable. And if the binding energy is less, it means that less energy is required to break up the atom and the atom is less stable. Also, if binding energy is negative, the nucleus is unstable and it will disintegrate by itself. Okay, so now that we know what binding energy is, let's calculate the binding energy of the helium atom. So in order to find the binding energy, we should know the mass defect. We already found the mass defect of helium atom in the previous slides, and delta M is equal to 0.0303774 and this is the mass defect of helium atom. So but we cannot substitute this directly into the E is equal to delta mc square equation, because in that equation the delta M should be in kilograms, but here we have the mass in atomic mass units. So we have to convert it into kilograms, and the conversion factor is 1U is equal to 1.66054 into 10 raised to negative 27 kilograms. So if we multiply the mass defect, that is 0.0303774 into 1.66054 into 10 raised to negative 27 kilograms, you will get the answer as 0.05044 into 10 raised to minus 27 kilograms. Now we can directly substitute this in the E is equal to delta mc square equation, where c is the speed of light and equal to 3 into 10 raised to 8 meter per second. You will get the energy to be 4.5396 into 10 raised to negative 12 joule. Now, if I want to express it in electron volts, then just divide it by 1.6 into 10 raised to negative 19, and you will get the answer as 28.3 into 10 raised to 6 electron volts. That is equal to 28.3 mega electron volts. Now, instead of doing all of these steps, there is a shortcut. There is a direct conversion factor. We can directly convert mass in atomic units to mega electron volts by just multiplying it by 931.3, and the conversion factor is 1U is equal to 931.3 mega electron volts per c square. So if you directly multiply the mass defect, that is in atomic units, by 931.3, you will get the binding energy directly in mega electron volts, and that's what I have done. That is delta M into 931.3 is equal to 0.0303774 into 931.3 is equal to 28.3 mega electron volts. So here you can see that in both the cases we got the same binding energy, that is equal to 28.3 mega electron volts. And I hope you guys now I hope that you guys know how to calculate the binding energy. That brings me to my last slide. So here I've got a bonus slide for you guys. It's about quarks. So what are quarks? Quarks are the fundamental constituents of matter. In the universe, there are about 6 quarks. six types of quarks, that is up, down, top, bottom, strange, and charm. So our proton consists of two up quarks and a down quark, and a neutron consists of an up quark and two down quarks. So what you have to remember here is that the up quark is lighter than a down quark, or a down quark is heavier than an up quark. Either way. So here you can see from the picture that the blue, the up quark, and there is an up quark and up quark, and the green, down quark and down quark. And the only thing different is the red, that is a proton has a U, that is up quark, whereas a neutron has a D, that is a down quark. So just now we saw that a quark is lighter, hence proton will be lighter than neutron, or neutron will be heavier than the proton. So I hope you guys understood everything. Thank you so much for listening to me. Now I invite my friend Anne-Marie to continue on with her presentation.
Today, I'm gonna take the topics binding energy per nucleon, nuclear fission, nuclear fusion, and packing fraction. What is binding energy per nucleon? Binding energy per nucleon is defined as the average binding energy of the nucleus. We use the equation binding energy divided by nucleon number to find out the binding energy per nucleon. For helium, the binding energy per nucleon is 28.3 divided by 4, which is equal to 7.1 mega electron volt. This is the graphical representation of binding energy per nucleon with respect to mass number. Here, the graph is plotted between binding energy per nucleon along y-axis and mass number along x-axis. We can see that the curve rises steeply at first and then progresses gradually until it reaches a maximum value of 8.79 mega electron volt at a mass number 56 corresponding to iron, and then it decreases. We can also see sharp increase in the binding energy for the nuclei of hydrogen, beryllium, carbon, and oxygen. For larger mass number, the binding energy decreases. This is due to the large Coulomb repulsions between the proton, making them highly unstable. Now, let's move on to the conclusions we get from the graph. From the graph, we had understood that the binding energy is constant for nuclei of middle mass number. This means that the binding energy per nucleon is practically independent of the atomic number for the nuclei having mass number between 30 to 170. Secondly, iron is having the highest binding energy per nucleon and it is more stable. This is the reason for the large abundance of iron in the nature. And we also understood that binding energy is strong for grouping of 4 particles. This is due to a pairing force which exists between a pair of neutrons and a pair of protons. The peaks in the figure at mass numbers 4, 8, 12, 16, 20 and 24 are clear evidence of this effect. And the last conclusion from the graph is that nuclei with very low or very high mass numbers have lesser binding energy per nucleon and are less stable, because the lesser the binding energy per nucleon, the easier it is to separate the nucleus to constituent atoms. From this, we come to the conclusion that nuclei with low mass number may undergo nuclear fusion and nuclei with high mass number undergoes nuclear fission. Therefore, in the graph, the part of the curve to the left shows that 2 light elements can produce energy by fusion, and the part of the curve right shows that a heavy element can produce energy by fission. Moving on to our next topic, nuclear fission and nuclear fusion. We all know that nuclear fission is a splitting of a nucleus of an atom into a nuclei of lighter atoms. In this process, there is a release of tremendous amount of energy. For this process, we commonly use uranium and plutonium. Nuclear fusion is the opposite of nuclear fission. This is the reaction in which 2 light nuclei combines to form a heavier and more stable nucleus. From this diagram, we can easily understand the difference between nuclear fission and nuclear fusion. Here, nuclear fission is the splitting of a larger atom into 2 or more smaller ones. And in fusion, there is a joining or combining of 2 or more lighter atoms into a larger one. Moving on to our last topic, packing fraction. It is defined as the ratio of the difference between the atomic number and the mass number to its mass number. It is also defined as the mass defect per nucleon. We use the equation atomic mass minus mass number, the whole divided by mass number to find out packing fraction. Packing fraction is mainly used for measuring the stability of atom. So that's all about my topic. Next, I invite Aneena for continue the section. Thank you.
Thank you, Anne-Marie. Now the topic assigned to me is nuclear density. It is a very simple topic and I think you all are familiar with it. So, nuclear density. Nuclear density is the density of the nucleus of an atom averaging about 2.3 into 10 raised to 17 kilogram per meter cube. The descriptive term nuclear density is also applied to situations where similarly high densities occur, such as for example with the neutron stars. The nuclear density of a typical nucleus can be approximately calculated from the size of the nucleus, which itself can be approximated based on the number of protons and neutrons in it. So, we can calculate the nuclear density with the help of the formula density is equal to mass by volume, where in this case nuclear density is equal to nuclear mass by nuclear volume, and here nuclear mass is equal to AMN, where A is the mass number and Mn is the mass of nucleon, which is equal to 1.67 into 10 raised to minus 27 kilogram. Nuclear volume is equal to 4 by 3 pi r cube, where r, the radius of a typical nucleus in terms of number of nucleons, is r is equal to a raised to 1 by 3 r0, where a is the mass number and r0 is equal to 1.25 femtometer, which itself can be calculated into meters by multiplying it with 10 raised to minus 15. So, the nuclear volume in the next step, we are substituting the value of r in it. So, 4 by 3 pi r, r0 a raised to 1 by 3 the whole cube. Now, the nuclear density is equal to mn, amn by 4 by 3 pi r cube. In the next step, we substitute the value of r. Now, a and a get cancels. So, the next step we get mn is equal to 4 by 3 pi r0 cube. Substituting all the values we know, we will get the answer as 2.8 into 10 raised to 17 kilogram per meter cube. From this topic, we must conclude 3 points. Nuclear density is independent of mass number of an atom, which means that the nuclear density of all atoms is same. The second point is that higher energy electron scattering experiments have established that matter is not uniformly distributed inside the nucleus. And the third point is density of nucleus is maximum as its center and decreases as we move outward from the nucleus. Now I have some examples for you. There is a question that iron has a mass number of 56. Find the radius, approximate mass and approximate density of the nucleus. But the only given value is mass number, which is 56. So we can find the radius, which is equal to r0 a raised to 1 by 3 by substituting the formulas 1.2 into 10 raised to minus 15 into 56 whole raised to 1 by 3. We get the answer as 4.6 into 10 raised to minus 15 meter. We converted femtometer to meter in this case. Next, we can calculate the approximate mass, the formula AMN, where A is the mass number and Mn we have 1.66 into 10 raised to minus 27. We get the answer as 9.3 into 10 raised to minus 26 kilogram. Now we can find density. Density is equal to mass by volume, where mass is equal to AMN divided by volume 4 by 3 pi r0 a cube raised to 1 by 3. So we get, by substituting all the values, we get the answer as 2.3 into 10 raised to 17 kilogram per meter cube. So we can find all the questions. We can answer to all the questions which is related to nuclear density. It's very simple topic. So that's all about my topic. Now I'm getting to Ria Rose. She will give you the next presentation. Thank you.
Nuclear spin. Now we are going to learn about nuclear spin. Nuclear spin is a nuclear magnetic moment which produces magnetic interaction with its environment. Electrons, protons and neutrons are spin half particles. Spin angular momentum of a nucleon is represented by S is equal to half 1 by 2 plus 1 power 1 by 2 h by 2 pi. The component of angular momentum is represented by Sz is equal to plus or minus 1 by 2 h by 2 pi. We know that nucleons have orbital motion in addition to spin motion, and hence there is a total angular momentum which is represented by J, called nuclear spin. Magnetic moment. Magnetic moment. The nuclear magnetic moment is the magnetic moment of an atomic nucleus and which arises from the spin of protons and neutrons. As it is a magnetic dipole moment, the contrapole moment causes some small shift in the hyperfine structure as well. Nuclear spin and magnetic moment. We know that electrons have magnetic moment. Likewise, nucleons have also magnetic moment. It is due to the angular momentum. Nuclear magneton is represented by mu n, which is equal to Eh by 4 pi mp is equal to 5.05079 into 10 raised to minus 27 joule per Tesla, where mp is proton mass, which is 1836 times me. Mu e is equal to mu b by 1836. Now I invite Leya to continue the session.
Thank you, Ria. Now let's discuss about nuclear forces. There are two types of nucleons present in the nucleus, which is the proton and neutron. The strong attractive force between the nucleons that holds the nucleus together is called nuclear force. Since protons and neutrons present in the nucleus, nuclear forces present are proton-proton force, proton-neutron force and neutron-neutron force. Note that it is a strong attractive force. It is also one of the property of nuclear force. You might have a doubt that proton and proton have like charges, so whether they will repel each other. Yes, it is true, but attractive forces between protons is greater than their repulsive force. Now we can discuss about the properties of nuclear forces. First one, nuclear forces are very strong. Actually, nuclear forces are the strongest among all the forces present in nature. Its magnitude is about 100 times than Coulombic force. Second one, nuclear forces are very attractive, which we had already discussed in the previous slide. And another property is they are short range forces. This means that each nucleon influences only those nucleons which are in its close vicinity. This property is also called saturation property of nuclear forces. The range of nuclear force is of the order of a femtometer, and 1 femtometer is 10 power minus 15 meter. Next property is nuclear forces are charge independent, which means protons and neutrons are having different charges, but the nuclear forces between proton-proton, proton-neutron or neutron-neutron are nearly same. So, nuclear forces are charge independent. Next property is nuclear forces are spin dependent, which means if we have two nucleons having parallel spin and another two nucleons having anti-parallel spin, when checking their nuclear forces they are different. So, nuclear forces are spin dependent. Next one, nuclear forces show pairs of pairs. That is, there can be interaction between pair of proton with pair of neutron. Last one, nuclear forces are non-central force or tensor force, which means the nuclear forces do not point along the line joining the centers. Thank you. So our presentation is over. These are very small topics and I hope everybody is clear with it. I thank Professor Pius Augustine for giving us such a wonderful opportunity, and I thank everybody who have spent your precious time with us. Thank you all.